Okay, so section 19.8 is kind of a fun one. We're going to talk about some of the ways that practical voltaic cells are constructed. Um, it's not a section, honestly, that I'm going to ask any questions about on any quiz or anything. And I don't imagine any sort of a question showing up on my exam either from this section, but it is kind of a fun one. So first practical voltaic cell that we're going to consider is the lead storage cell. And this is like a battery that you would have in your car, on a boat, or a recreational vehicle. This is the deep cycle lead acid battery that is pretty ubiquitous. Sorry, I'm just noticing that my face is half cut off, and I swear that's a little different than it was yesterday. I think my camera's tilted a bit. That's okay, doesn't matter. So in the lead acid battery, you have an anode reaction. I know I don't have a lot of room here, so I'll try to write it small. Of lead solid plus sulfate ion aqueous, and that's going to form lead sulfate, which is a solid, plus the 2 electrons that are released by oxidizing the solid lead to form lead 2 plus ions. Sorry, I'm bothered by my half face there. That's a little better. Okay, and the cathode. Make sure that's not cut off, and it isn't, is going to have lead oxide. This is lead 4 oxide plus sulfate again. And, shoot. Okay. And 4H plus aqueous, and then the 2 electrons. And that is going to form lead sulfate as well, which is a solid, plus 2 waters, plus 2H2O liquid. That ran a little bit off of the screen. But what's really interesting about this cell is that all of the redox active species are solids. The lead solid goes to lead sulfate solid in the anode, and the lead 4 oxide solid goes to the lead 2 sulfate solid in the cathode. And so if you look at the figure here showing the lead storage cell, you have an anode that is made of solid lead, and it's got some lead sulfate solid coating kind of around it near the bottom. And then the cathode is an inert electrode. I don't know what they use, probably carbon or graphite. And then packed into just like some holes or voids in that electrode is the lead 4 oxide. And then there's lead sulfate solid that forms kind of around the bottom outside of that electrode as well. Anyway, the point is that because there are no actual lead 2 plus ions in solution migrating back and forth, there's no creation of new ions, or at least no lead ions, or reduction of lead ions in the solution. This means that there's no need for a salt bridge, so you can place both the cathode and the anode in the same concentrated sulfuric acid container. That simplifies the construction of the lead storage cell. And not only can you put the cathode and the anode in the same concentrated sulfuric acid solution, but you could actually put several pairs of anodes and cathodes, hook them up in series, and this is just like when you have something that has several batteries that you place end to end in order to get a higher voltage. Okay, within a lead acid battery for, say, your car, I forget how many individual anode-cathode pairs there are, but I think it's like 3 or 4 individual batteries that are all sharing that same concentrated sulfuric acid solution. They're wired up to be in series, and so like your one battery is actually several cells built into one together. Anyway, it's really clever engineering, really cleverly designed so that it's a simple and reliable cell. You also, if you have concentrated sulfuric acid, the only ion concentrations that will change are the sulfate and the H+. And if those concentrations are high to begin with, then the voltage that is output by this battery won't change very much over a discharge cycle. And so that's also a good positive to this sort of a voltaic cell. The voltage, even as it discharges, the voltage remains relatively constant. Okay, so that is the lead acid storage battery. Give me a sec here, we'll get to the next one. I've got to skip quite a few slides. I don't want to overshoot it. I think that did it. Okay, the next is the dry cell. I'm going to go ahead and erase up here because it's got the chemical equation on there. So this is the first type of dry cell, which is like the little batteries that you put in your electronic devices. It's called a dry cell because instead of having an aqueous solution, a salt bridge and an anode and a cathode with aqueous solution, instead it's going to have electrolytes and mobile ions packed into a gel or a, what's the word they use? Sorry, give me a sec. A paste or a gel. This makes it safer. You know, if you had a battery that had an aqueous solution, then any small bit of damage would cause it to be leaking acid everywhere. And you've probably experienced a dry cell battery leaking acid, but it only does so if it's, you know, pushed beyond certain limits. And generally speaking, it's a lot safer than if it were an actual wet cell with aqueous solution. Anyway, the example that they give here has zinc being oxidized at the anode, and then manganese being reduced at the cathode. And this was the first commercial type of dry cell battery. Of course, there is an abundance of different kinds now: nickel metal hydride, rechargeable alkalines, lithium polymer, lithium ion, and lithium cells. They're all technically different in their chemical reactions, but we're going to use this as a representative example of how most dry cells are constructed. So the salt bridge is usually a thin piece of paper. They call it a porous separator in this figure. And usually it's just a piece of paper that's kind of wrapped around the inside of the anode, which is the actual body of the battery. And then the cathode is inside of that with some sort of a gel or a paste that contains cations to be reduced. The first dry cells had an acidic paste, and later ones were developed that had a basic paste, and that's why they're called alkaline batteries. Of course, all of the batteries that I grew up with are basically obsolete these days. I don't know if you even are particularly conscious of the difference between alkaline batteries and non-alkaline batteries, because they've really all been superseded by the lithium polymer battery, which I'm going to talk about even though it's not really in your textbook. Lithium ion polymer cells are now ubiquitous. They're in laptops, cell phones. They're even in Tesla cars. And so in a LiPo cell, no metal cations are actually reduced and no metals are actually oxidized to form cations in the common way. Instead, you have an anode and a cathode which are both a polymer matrix that carries a permanent charge. So what I mean by polymer matrix is that a polymer is a long molecule. We'll actually talk about polymers next week sometime, or 2 weeks maybe. But it's a rigid structure that has open spaces that smaller molecules or ions can pass through. And so the anode, hold up, I wrote this down so I can make sure that I don't say it wrong. Okay, the anode has a polymer matrix that carries positive charge. And so when you charge a lithium polymer cell, lithium plus ions, so here we go, anode, it looks like this. It's got a polymer matrix and it is positively charged. I know this is a little sloppy, but there's positive charges right there. And when you charge, those lithium positive ions are forced to intercalate into that polymer matrix. Of course, they're both positively charged, so they don't want to go there. That's why you have to provide a power source, say from your USB charger, to force those lithium ions to enter into that lithium anode polymer matrix. And then at the cathode, you have another polymer matrix, and it is negatively charged. So when, I'm going to erase this little arrow, because what happens as the battery discharges is that these lithium ions are going to migrate from the anode into the cathode, and they will begin to intercalate themselves into that negatively charged polymer matrix. And of course, this is a spontaneous process. The cations are attracted to that negative polymer matrix. But remember, we talked last time about how electricity is not just the flow of electrons, it's the flow of any charge at all. And so if these lithium ions are physically migrating from the anode to the cathode, then they're going to cause a complementary migration of electrons that will match them, traveling through the external circuit and powering your phone or other device as the lithium polymer battery discharges. So LiPo cells are so popular now because they have a high energy density. They are reliable to charge and discharge many, many times. They charge quickly. They're really a great innovation, and a lot of the ubiquitous electronics around us today couldn't be possible without the LiPo battery. So we should be really grateful that it was discovered and developed. Okay, 1 second. Sorry, I'll set up the next slide. There it is. Okay, so the next interesting type of voltaic cell is called a fuel cell. And so really any sort of a electrochemical cell can be a fuel cell. Technically, the definition of a fuel cell is any electrochemical cell where you continuously replenish the reactants. So suppose you had our zinc copper cell that we were looking at so much last week. The copper ions are being reduced to form solid copper as it discharges, and the zinc electrode is being oxidized to produce zinc ions. Well, if you replaced the two beakers with say pipes that would constantly flow fresh copper 2+ ions past the cathode, and it would constantly wash away the zinc 2+ ions away from the anode, and maybe had some mechanism that would feed zinc wire in the anode down as it's degraded. Well, anyway, you can imagine how you could construct a cell that runs indefinitely because you're replenishing the reactants. Okay, so technically that would be a fuel cell, but in practical terms, Fuel cells that are built and used today tend to take advantage of combustion type reactions. And so if we consider this reaction, 2H2 gas plus O2 gas forming 2H2O gas, that's a combustion reaction. It's not like methane or gasoline or whatever, but it's a combustible material with oxygen forming water. It's technically a redox reaction. Right? We go from 0 oxidation states on the hydrogen and oxygen to +1 and -2. So it is a redox reaction, and it can be carried out in such a way that we separate the half reactions into a cathode and an anode. So let me go ahead and rewrite the full reaction in terms of its two half reactions. At the anode of a hydrogen fuel cell, you're going to have H2 gas forming 2H plus aqueous plus 2 electrons. And at the cathode, you're going to have oxygen gas plus 4H plus aqueous plus 4 electrons forming 2H2O gas. So you can separate these two half reactions, and you see there a diagram of a hydrogen fuel cell where the H plus ions that are generated at the anode will physically migrate across an electrolyte barrier through to the cathode, where they can participate in reduction of oxygen and generate water. So this needs to be constructed with a membrane that will prevent hydrogen itself and oxygen itself from straying outside of their own half cells. But and also this reaction is one that typically requires a high activation energy. For example, if I were going to explode a hydrogen balloon, I'd need to use a match to start that reaction going. So in addition to a selectively porous membrane separating the two half cells, you'll usually have at both electrodes some sort of a catalyst, a platinum or a rhodium catalyst, and those are expensive precious metals. So hydrogen fuel cells are not cheap to build. However, they can give a tremendous amount of energy, and as long as you keep the hydrogen gas and the oxygen gas flowing across those electrodes, then it can also run indefinitely. You can use a hydrogen fuel cell to generate electricity in a generator, or you can then use that electricity to turn a motor. And so hydrogen fuel cells are an attractive option for a new type of electric vehicle where you don't have to recharge your battery, you just fill a tank, just like we do with modern gasoline internal combustion engines. So there are hydrogen combustion cars that you'll see around on the street sometimes that just burn the hydrogen in an engine, just like most engines burn gasoline. So a hydrogen fuel cell car is technically different. It doesn't burn the hydrogen to produce heat and use that heat to move pistons and convert that to mechanical energy. Instead, it uses the hydrogen and oxygen in a fuel cell to generate electricity directly, and that electricity will directly turn an electric motor. What's interesting is that by doing it this way, you have a much higher theoretical limit to the efficiency of a hydrogen fuel cell engine compared to a hydrogen combustion engine. And so that's what makes these a really attractive option. Of course, you don't see them around very often, if at all, And that's because there are other engineering problems to overcome, like how to construct the fuel cell more cheaply and how to store the hydrogen safely and effectively. Hydrogen is a lot harder to carry around in large quantities than, say, gasoline. Gasoline you can stick in a red plastic jug and you've got a whole lot of energy that is stable and easy to carry. No, hydrogen gas, because it is a gas, presents a lot more problems. Let's see, and again, sorry, I should have made this perfectly clear. As the H plus ions migrate from the anode to the cathode, that is an electric current. And so it will induce a complementary electrical current through the external circuit by causing electrons to flow from the anode to the cathode, just like the lithium polymer batteries. Both LiPo batteries and hydrogen fuel cells no longer have a salt bridge because the ions that flow are actually a part of the reaction instead of these inert ions that form the salt bridge. Okay, the last part of chapter 19.8 has to do with corrosion or rusting. Let me quickly jump over to figure 19.14. Okay, so this figure shows how iron will rust. You're probably aware that, like, when iron tools get wet, they rust more readily than an iron tool that is dry. And the water mediates that by providing a way for ions to physically travel from one spot to another. And most of the time when something gets wet, there's going to be some salt that's dissolved in that water that can act as an electrolyte, like a salt bridge. And most water is going to be at least slightly acidic or slightly basic. Rainwater, for example, is usually acidic. And having that H plus concentration is going to be essential to mediating the oxidation of iron metal. So you see, when something does rust, not only is the iron turned into iron 2 plus ions, but those iron 2 plus ions will then go ahead and reduce oxygen in the air around us to produce oxygen 2 minus, and then they combine to form insoluble iron oxide. And that insoluble iron oxide can be generated at a different physical location than where the iron was originally dissolved. So not only are you converting iron to iron oxide, but you're also roughening the surface. You're causing corrosion in one location and deposition of the iron oxide in another. And the result is the rough, flaky, rusty texture that we're familiar with. You know, a tool that's left out in the rain, it doesn't just turn from silver to red. It gets all it gets rusty in texture, and that's because of as you see, the iron oxide is deposited at the water-oxygen boundary, but the iron gets eaten away at anywhere that's covered with water. Anyway, so this is corrosion or rusting, and it can happen to all sorts of metals. Of course, we've already seen the electrochemical series in several different forms. Way back in 1210, we saw that electrochemical series making qualitative comparisons, and then last week we saw the table of standard reduction potentials. And so we know that some metals will corrode more readily than others. And that actually provides a basis for a way to protect our metals from rusting. So this is called cathodic protection. If you have a metal that is vital that you want to protect, then you should put it in electrical contact with another metal which is more readily oxidized. So zinc is a common one because it's inexpensive and it's easy to work with, and it oxidizes much more readily than iron or other metals that we like to use in our tools and things. And so when you have zinc in contact with iron and say some water gets on it and the conditions are right for a redox reaction to occur, because of its higher oxidation potential, the zinc is going to be oxidized first, preferentially and first, and that will protect the iron itself. So we call this cathodic protection because the iron kind of acts as an inert cathode, which will reduce the oxygen without being corroded itself, while the zinc is a chemically active anode and dissolves away to form zinc 2+ ions, but we don't care about that because the zinc was never a structurally important part of our tool anyway. So the zinc is often called a sacrificial anode because it is reacted away in place of the cathode, the iron that we care about. And so when corrosion occurs, it is the sacrificial anode which is oxidized, leaving the vital iron intact. So you may have heard of galvanized materials, galvanized steel. You'll see galvanized screws and nails and galvanized sheet metal and whatnot. So galvanization is the process of coating steel with a thin layer of zinc in order to protect it against oxidation. You'll recognize galvanized materials because the zinc is deposited in a thin layer through an electroplating process. And we'll talk about electroplating in just a minute here. But the zinc outer layer will show these really cool crystal grain boundaries. It'll look like the metal has a mosaic pattern. And what that is different regions of zinc that just have slightly different crystal alignments. And that's how you can recognize a galvanized material. So sometimes it's called cathodic protection, sometimes galvanic protection. It's an important way to protect a metal that would otherwise corrode in the presence of water. Okay, like I said, I don't really have any questions about this. I just think it's really fun and interesting to have a deeper understanding of how the electrochemistry around us works. I mean, every day we're within 5 feet of probably a half a dozen different electrochemical cells, and now you know a little bit about how they function.